My name is Kaustubh Simha. I'm a first year, and I'm working with Sean Doan, who's a fourth year, and our project is doping quantum materials. First, let's give an introduction on semiconductors and doping. Semiconductors are materials that are a staple in modern technology. By simply adding electrons, negatively doping, and taking away electrons, positively doping, we can make these materials more metallic or insulating. Transistors are also essential in today's computing. They act like on and off switches and are simply a piece of semiconductor that is partially doped. And they are the building blocks of all digital logic components today. In our project, we aim to use two-dimensional atomically thin quantum materials to make transistors. For our base semiconductor, we are using monolayer tungsten diselenide. And for our positively doping agent, we are going to be using ruthenium chloride monolayer. By using our method of two-dimensional atomically thin quantum materials to make transistors, we're able to make much smaller transistors than the convention. This means we're able to fit more transistors in a certain area, allowing our everyday devices to have much more computational power. Also, the materials we plan on using are extremely easy to work with and maintain. Here's actually a picture of our sample that is loaded up in our optics table, ready for photoluminescence measurements and Raman spectroscopy measurements. It is actually a base monolayer tungsten diselenide that is partially covered by our p-doping agent ruthenium chloride monolayer. On our optics table, we also do have access to a cryostat, so we plan on doing temperature dependence measurement. This cryostat goes down to about 3 Kelvin, and this is just to see how a change in temperature would affect the doping of our sample. And we plan on finishing all our measurements by April 19th. The stacking process and how we made our sample is very, very simple. We first dropped the monolayer tungsten diselenide that was exfoliated on PDMS, a polymer, onto a substrate silicon, and then partially covered it by a monolayer ruthenium chloride. Both these monolayers are attached to each other through the van der Waals forces, and this process is extremely simple.